Moving on to next topic, law of conservation of momentum. This topic precisely should be law of conservation of linear momentum. Now what it states is, in an isolated system, total momentum remains conserved, irrespective of the fact that, no, this is not in the statement was that's it, that total momentum in an isolated system remains conserved. What it means is, momentum, there is no change in momentum, or irrespective of the fact that there might be some action or reaction forces due to mutual interaction of the bodies of the system. That means if I have a system of this room, suppose this room is a system, and there are two bodies, two big spherical balls which are colliding and they are going apart, then where the net momentum, that is the total initial momentum, will be equal to total final momentum. That is, total momentum will be conserved, and it will not depend on the fact that these bodies are mutually interacting, okay, by action and reaction forces. So let's prove it. Consider a system having two bodies of mass m1 and m2. All right. Let us say the initial momentum of this body is p1 and initial momentum of this body is p2. Let them collide for a very small time interval delta t. That means they are mutually interacting. All right. And after that they are moving with some other velocity. There is some initial velocity, you can call it u1 and u2, and now at the final stage, they, after collision, they are, that is m2 and m1, they are going with some other velocity, let us say v1 and v2. Okay, so final momentum of the system, let it be P1, I have taken P1 here, so P1 dash and P2 dash. This is the final momentum of this body and final momentum of this body. Now, according to law, the net momentum is conserved. How we are going to prove it? We know, according to Newton's second law of motion, don't write like this, according to Newton's second law of motion, what do we have? Force is equal to rate of change of momentum, right? So change in momentum, what I am going to write is force is equal to change in momentum upon time. I am multiplying time with the force, so I will be left with force into time is equal to change in momentum. So force on 1 due to 2, if I call this body body A and body B, so force on body A due to body B will be change in momentum upon time, but I am multiplying time here because delta t is a very small time during which the body interacted. So this will be equal to change in momentum of body 1, that is body A. So force on A due to B is P1 dash minus P2 dash, right? Is this statement right? This is the change in momentum of the body A. Very good, this statement is not right. It should have been final momentum minus initial momentum. So P1 dash minus P1. P1 is the initial momentum of this body and P1 dash is the final momentum of this body. So final minus initial. Similarly, force on body B due to A into delta t will be equal to final momentum minus initial momentum. So that is P2 dash minus P1 dash. Now we know that according to Newton's third law, which we have already proved that Newton's third law, action is equal to reaction and they are in opposite direction, FAB will be equal to negative of FBA, right? I have still done a very minor mistake in this whole process. If I am taking the vector form here, I have to take the vector form on right hand side as well. So they all should be represented in vector form, this much. Now, using this, if I replace FBA with minus FAB, what will I get? If suppose from here suppose here, instead of FAB I am writing minus FBA, what will I get? This equation will become minus FBA into delta t will become this thing, P1 dash minus P1, right? This is correct. Instead of this term I have used Newton's third law, and from this equation I have put it here. Now what do I have now? FBA into delta t, the same term, so I am taking the negative side here. What I will be left with, this thing becomes F BA into delta t is equal to, taking negative side here, negative of P1 dash minus P1, right? So use these two equation this and equation this. Both sides LHS is same, FBA into delta t, so the RHS has to be equal. So P2 dash minus P1, it should have been P2, right? P2 minus should have been P2. Yeah, change in momentum of the second body. So P2 dash minus P2 is equal to this thing, negative of P1 dash minus P1, right? All in vector form. So here I get P2 dash minus P2 is equal to minus P1 dash plus P1. Taking this thing here and this thing here, what will I get? This was dash. What will I get? P2 dash, this thing is there, plus P1 dash is equal to P1, or I am bringing this part here, the P2 here, this will become positive, P2 plus P1. So what did I get now? This P1 plus P2 is total initial momentum, this plus this, right? This is total initial momentum of the system, and P2 dash plus P1 dash, that is this thing and this thing, this is total final momentum of the system. So from this equation, total final momentum is equal to total initial momentum, and that is why this thing proves the law of conservation of momentum, that is total momentum or total linear momentum of an isolated system remains conserved. Now I'll apply the same technique, same method on a concept which is called recoiling of gun. See, this time I'll be using the final and initial velocities, and we will find the recoil velocity of gun. How? See, when we fire a bullet from the gun, what do we feel? We feel a jerk. If we have not tried it practically, we have seen in the television that whenever a soldier fires a gun, he feels a backward side push, which is called recoiling of gun. So recoiling of gun, the velocity of recoiling of gun is in negative direction of the direction of bullet. So this is what we are going to prove right now. I'll be using this thing, the same thing, or rather I can use a different concept, but let us try it out from this thing only. Okay, total initial momentum according to, this time I'll be using according to law of conservation of momentum. Total initial momentum of the system was m1 u1 plus m2 u2. This is equal to total final momentum of the system, that is, now they are moving with velocities v1 and v2, m1 v1 plus m2 v2. This is total initial, this is the initial momentum of body A, initial momentum body B, total initial momentum of A, initial momentum of B, no, final momentum of A, final momentum of B, and this is total final momentum. So total initial momentum is equal to total final momentum. This is what was stated to us by law of conservation of linear momentum. Now what do we have? Just in case, this is a expression which you can be using, which you will be using in lot of numericals, alright, and in lot of concepts, but right now I am talking only for the recoiling of gun thing. So what is total initial momentum? Total initial momentum is 0, right, because initially both gun and the bullet are at rest. When we fire the bullet, suppose this is gun, suppose m1 or m2 relates to gun. Okay, let's do one thing. This is the whole statement for law of conservation of linear momentum when it is applied in numericals, and I'll explain you the recoiling of gun in a while.